Good afternoon, everybody, and welcome to another Geo-Institute live stream. You have found it. You're back in 2 days as part of the Geo-Institute Summer of Live. I'm Brad Keeler, the director of the Geo-Institute, and we're thrilled to welcome you into episode 9 of our quarterly publication series called Books Rock. See what we did there? Rocks, Earth, Geotech. Ha 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 ha. I know you're all laughing with me. If you don't know anything about the Geo-Institute, after you watch this today, you should head over to geo-institute.org on your favorite internet-connected device, and you'll find out all kinds of things about us, including that we're a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, Dimitrios and Tim have painstakingly crafted their presentation to ensure that you do like what you see. When you have those feelings, you should click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. We have 2 props for you today. One is atop my noggin here. It is my ASCE 2027 hat with the multi-shield on the front and the GI shield on the side. It's got the conference URL on the back, meant to remind you that next year Geo-Congress will be part of ASCE 2027 along with Structures Congress, the CI Summit, EWRI Congress, and several other institutes and people across ASCE will be organizing this amazing first of its kind event. You want to be there. Registration opens later this summer. You can get exhibit and sponsorship opportunities on the website right now to make sure that you are there. We also have Ralph Peck with us today, bobbling away. Shout out to Tim, who once lived in Ralph Peck's house. That's an amazing story. If you haven't heard it, you can go back on the YouTube channel and listen to that. If you have not yet made your contribution to GI student programs for 2026, it's a great time to do so. When you're at geoinstitute.org, just click the little tab that says student programs or student participation fund or something of that sort. Go in, make your donation, and we have amazing thank you gifts. For $96 or more, you can have a Ralph Peck bobblehead to display proudly on your shelf. I mean, you could carry it around, but it's probably better to put it on your shelf. We have quarter zips for $250 and a million other thank you gifts that we can give you. I mentioned at the top that this is our publication series, and so here with us today from the adroit publications team in ASCE to tell you a little bit about the publication you're going to hear about today, it's something special, is Leslie Connolly from the publications team. Leslie, take it away.
Thank you, Brad. Okay, so I put up on the screen the book that we're talking about with a QR code and a discount code. ASCE, as you may know, is the leading publisher of civil engineering content. We publish books, standards, conference proceedings, as well as journals. Today, we're talking about this technical report from the Geo-Institute's Embankment, Dams, and Slopes Technical Committee, Highway 1 Rat Creek Embankment Failure. Provides details of the team's investigation, including data collection activities and recommendations to avoid embankment erosion. So get online and buy the book. I'll turn it back to Brad. Thank you.
And be sure to use that discount code. We'll put it in the chat so that you can, as well as the link to the publication so that you can do that. But as a reminder, as soon as this presentation ends today, it's archived to the YouTube channel. You can come back and watch it as many times as you want. You can go find that code over and over and over again if you need to. Today, we're really excited because before we hear from Dimitrios and Tim, we have a first-timer on the GI live streams who's going to moderate for us today, all the way from the left coast of America, where he works at Turner Construction. It is Santiago Caballero. Santiago, welcome. Thank you for doing this today.
Thank you, Brad. Thank you. It's a pleasure to be here and an honor to be moderating Tim's and Dimitrios' session. It's just amazing work that they did with the GSP. And I'm happy to be here again. I can introduce myself in a little bit, but happy to be here. I just go on, roll it on. I guess
You're
that's
on.
me.
Yep.
All right. Well, again, I'm Santiago Caballero. I'm a geotechnical design specialist here at the Turner Engineering Group, working at Turner Construction. I've been working as a consultant for a few years in the past, and now working on the contractor side. Always liked the geotechnical world, and then I read this geotechnical special publication from Tim and Dimitrios, and it's just an amazing recon and analysis work that you guys did. Tremendous work, field work, and then after that, you guys did a lot of office work, and then analysis that help the industry to continue monitoring the creeks and monitoring the embankments, and then helps also the dams engineering society and all the teams that are working together in this field. So again, I'm happy to be here moderating this. I have a lot of questions. I know you have your presentation up ready to go, but maybe I can start with a quick question. This Rat Creek was one of the EDS committee recon efforts that you guys did as part of the committees. What made this failure stand out for you to think that it was something worth it to document? Do you remember any kind of events, kind of the first time you saw the site or the photographs that kind of caught your attention, and you guys were like, well, this needs to go into a special publication because of all the things that I've seen like right away? Just question for both of you. We can start the conversation from there.
Okay, Dimitrios, I'll kick it off and jump in. So I was chair of the Embankment Dams and Slopes Committee at the time, and we had started a reconnaissance program for extreme embankment and dams and slope events. And of course, this is a very big slope, very important slope, as you'll see in just a minute. And it combined a number of hazards, not just slope stability. We knew that there was a fire there, a wildfire previously, and of course, a lot of rainfall. And that resulted in a debris flow you're going to see. So I thought it was a perfect case to investigate. And of course, I spent some time out in California, so I knew exactly where the site was. And so I felt pretty comfortable about getting there and getting some people there. So Dimitrios, why don't you jump in?
No, I got involved. I had seen about this failure, and frankly, through the media, and we're going to talk about what it looks like versus what happened actually. That it looked like a fantastic failure that was really important. And so when the team at some point contacted me, said, "Yo, you're there, basically. And do you want to get involved? Our committee is very interested in looking into this." And I said, "Yeah, I'll be very glad to contribute." And we took it from there and built a team. A really good team that helped us put this together, for sure.
Then I do apologize, but there's some students asking me, where is Tim and then where is Dimitrios? And I apologize for not introducing. You guys asked me to keep it short, but Tim is a professor of civil engineering at the University of Illinois, and Dimitrios, of course, is a professor of the civil and environmental department at the University of Berkeley, California, Berkeley. And then, I can keep it short. I can keep talking about you guys all the time because you guys do like an amazing contribution to the industry. And then like this publication right here. And I've read your work, have followed your work continuously. And then it's just amazing the contributions you guys make. So just a parenthesis here.
Yes.
And then you guys continue maybe. Team, you can pull up your presentation and then we can go through the entire work you guys did in this Rat Creek Embankment Failure.
Okay. All right, Santiago, can you see my screen?
Yes, we can.
Okay, let me get into presentation mode. Okay, I'm going to start off and just kind of give some introduction, and then I'm going to turn it over to Dimitrios, and then I'll come back at the end. So here we go, Highway 1 Rat Creek Embankment Dam Failure. Oh, let's see. So as I mentioned at the top, the Embankment Dams and Slopes Committee started conducting some reconnaissance trips when I was chair of the committee. And our first trip was in 2018 to Rattlesnake Ridge near Yakima, Washington. Still an active, very active and large landslide that's occurring there. Next was Hurricane Florence in 2018, Edenville Dam in Michigan in 2020. And I think, Dimitrios, you were also involved in that one too, right? Yeah.
Yes.
And then in 2021, Hurricane Ida, and 2021 also the Rat Creek embankment failure that we're going to talk about today. So that's how we sort of got into reconnaissance trips through the EDS committee. And we were really focused on interested embankment, dam, and slope case histories. And Rat Creek is one of those. Okay, so here's the outline for the presentation. Right there, 2, 4, 6 bullet points. And here's the cover page of the GSP. So one reason we were very interested, I was working on a project with the USDA on cascading hazards, and I think Dimitrios was also working on similar topics. And Rat Creek presented a unique combination of cascading hazards, and started with the Dolan fire right here in red. And then after the Dolan fire came a large precipitation event called an atmospheric river. And that led to collapse of a natural tree dam, which Dimitrios will describe in more detail, but you heard that right, a tree dam. And the breach of that dam led to a major debris flow overtopping Highway 1 and eroding the embankment supporting Highway 1 you see in the lower photo. And so, Dimitrios, I'll turn it over to you.
Sure. Yes, absolutely. So I think this is the team that contributed, were the two presenting today as the co-leads of that report. But everybody that you see here participated in the field. I'm not going to mention them by name, but you can see them and contributed to this report. And it is a team of engineers and geologists and also representatives from Caltrans, Ryan Turner for sure, a number of students also. And so this, what you see today is kind of the outcome of all these people's work. And this map has also the location of the Rat Creek, locations basically along Big Sur on Highway 1 between Monterey and San Luis Obispo. Yeah, I can go to the next one maybe. And feel free to jump in and think on any of those. But talking about what we think we see versus what happened. When, you know, on the top right is the figure you will see in CNN and other media when the failure happened. And when I saw that, I thought I was looking at a wedge failure, the type of thing we see in rock mechanics, and said, "Oh, that's a fascinating wedge failure." Had nothing to do with what actually happened at the end, as Tim kind of described. And we know that for a fact because there is photos actually. As we started getting involved, there was photos of the overtopping of the embankment and the gradual washout. So we have a number of photos as the roadway was washing out, as the rain fell on top of the embankment, it was eroding it gradually. And the photos at the bottom show that. The next slide. Yeah, and this is photos they're showing actually the erosion. Yeah.
Yeah.
And so these are just some more pictures. This is what you will see afterwards. This is a photo from Caltrans after the failure. The next slide also shows another view of that. And then as you get closer, you can see there is basically clear the erosion marks. You can go to the next one. And this is like the overview. So if you start paying attention back to this photo, which, as I said before, looks like a wedge, there is all this debris in the back of that washout. And then you may not have noticed, but there's all these wooden tree trunks, actually, that really piled against the road. And that's definitely part of the story. So we'll talk about that next. So if we go to the next slide, the first thing we did was to understand what failed, what moved, what happened. And so I think these are techniques that we extensively use nowadays, but we basically use the UAV structure from motion and some pre-existing LiDAR data. So there was LiDAR data before the event. And if you take the difference between the 3D models created by these two techniques, you can actually calculate volume of things, dimensions. And so you can definitely see there was significant elevation loss and a total volume loss of about 18,000 cubic meters. And that's what we measured. So that's the facts. And then if we go to the next slide, we can see some of the specifics about what happened that day. Basically, the Highway 1 is clearly closed. Both the lanes are completely gone. The highway remained closed for 85 days before Caltrans was able to fix it. And frankly, this was a quick repair, an impressively fast repair in my mind. It did cost, though, $11.5 million. Resulted in a detour of that was significant. You could no longer cross over on that highway, and so that's significant. And as Tim said before, we knew already that there was a fire in that area. About the fire actually had stopped a few months before that event. There was just the presence of fire-affected area, hints to increased water flow, potential triggering of debris flows, and overall due to the lack of vegetation and the damage done. And at the end, the culvert that was below the highway was damaged, and we'll talk about that. And without the presence of that culvert, without the operation of that culvert, the water ran on top of the embankment and started the erosion. But if we go to the next slide, the story didn't start on that day. It's as Tim said, and that came, we presented from the beginning, but as a cascade, but it wasn't immediately clear at that time, right? And so it's important to think about this when we have an event like that. How rare is it, and did that happen before? And one thing that had happened in that exact location was in 1985, there was another wildfire, the Gorda wildfire. And actually that one triggered a debris flow at that location. And that debris flow buried the existing culvert that was 66 inches, a very large culvert that was completely buried by that debris flow. That's 1985. And then, you could try to dig everything out and repair. That's kind of expensive. At that time, Caltrans said, we're going to install a vertical riser, which is 36 inches in diameter, so smaller. And we're going to actually not dig that stuff out, but let the water drop through the riser and find the culvert that is buried. And we will get back to fixing this. In fact, Caltrans had a plan to come back to that location and do a permanent, what they call a permanent fix. But of course, the events of the 2021 happened. And we have actually a photo of that riser just before the failure. It was operational. And so this is the 1985. We go next slide. Fast forward to 2020, the Dolan wildfire was in the news. That was a huge wildfire, covered a very large area, 500 square kilometers. And Rat Creek is on the top left of that affected area, and it was partially, not fully, but partially burned by the Dolan fire. And so the event was huge. That happened on August 18. The fire was burning actually for several months. I believe it was controlled in December of 2020. 2 months later, and the next slide, we have an atmospheric river. The atmospheric river is a storm event that affected that area. That atmospheric river stalled on top of this exact location of Rat Creek, south of Carmel. And we have precipitation data. There's 2 stations that are relatively nearby, plus the IMERG, which is a precipitation data set from NASA that really gives us information about the amount of water that fell on that area during the January 27 to 29 atmospheric river. It's about 300 millimeters, so about 12 inches that fell within a couple of days. And we have a very good time history of that. That precipitation, if we go to the next slide, fell on top of the wildfire affected area. And so our job was to actually go there and collect data and see what happens. So we can see a few pictures of on the data we collected in the next slides. So the one thing to recognize, and I think it's important from a resiliency perspective, is that in this case, the roadway is on the receiving end of all the action. Things are happening upstream from the highway, and the highway has to be able to handle those. And so the story of resilience is not just about where the highway is, but also all the area that leads to it. And we know that philosophically, but sometimes it's easy not to remember all that part. So we actually, when we visited the area, we started from the highway and headed upstream, basically, to see what happened. As we said, we knew there was a debris flow, and we started heading upstream. So the next slide will show that. This is the heading upstream. This is the highway and the debris flow. We can already see it. The figure on the left shows in the report various stations. We walked all the way to the beginning of the debris flow. And if you do go through the report, you will see lots of pictures about what we have for each of those places. And we have a few slides of that. If we go to the next slide, this is we're going to start walking upstream of the area. This is very close to the highway, just before, just above where the placement of all the debris came in. And you can already see a 2-meter scour zone, like a significant 6-foot scour that was taken out material from the debris flow. You can see also a cleaned rock at the bottom, the Franciscan melange that is down there, and it's actually very, very visible. So the debris flow took out everything that was placed, the soil that had been naturally placed there. A bit further upstream, if we go to the next slide, you can see another location, a similar story. There is, again, about a 2-meter, 1.9-meter scour. And what is really interesting to recognize is that we are there after everything has happened. But there is evidence of what was happening in stages in between that phenomenon. There is, you can see permanently, not permanently, but during the storm, submerged portions of this whole area. And we calculated there was about 3.6 meters of water that was actually completely overflowing the whole area on top of that scour. And then there were additional several meters where it was splashing of water. And so you can imagine being in that area at that time, very, very scary and very, very high energy and intensity. And we're only seeing the evidence at the end. Next slide has another station where we were looking at this. This is an example of another place where you can see a tree trunk possibly could have fallen during the storm, maybe not. We don't know exactly that, but what we do know is that it was completely submerged. There is evidence of water all over it, and there is actually debris against it in some places. So we know that this tree trunk that is actually up there was actually at some point below water. Next slide. Is another station. This is Oz Kozatsi, who is one of our team members, a geologist, who did a really great job in actually mapping. Once you have this section of the soil that has been removed by the debris flow, you can go on the sides and actually map to see what the story of the soil stratigraphy is. And he did a great job on that. And I think the next slide describes some of his work related to this. We did carbon dating to see the different horizons and how old they are. I think there are two main lessons from this. Number one is that we found repeated horizons, soil horizons, repeated places where there was burned material. So this was not the first wildfire. The 1985 was not the first wildfire, but we have a record going back 300 years almost, and we can see wildfire affected ground. And also we could see flood events, and we were able to date those. And there is a pattern to this. The most recent flood events are about 36 years apart, which do seem to be, compared to the previous horizon, faster than previous flood events. And we can discuss what that means. But maybe we can go to the next slide. As we walk up the debris flow, we wanted to go to the beginning of it. We thought we will find what is a typical scar of the initiation of the debris flow, but that's not what we found. And so what we found was a naturally placed tree debris dam. And Tim, you can go to the next slide. And that tree debris dam was placed by Tim, if you can go to the next slide, was pretty big. It was damaged by the time we reached it. This is a picture, if you can see it very well. We're going to have some annotation, you will see it. But it was damaged, so it was broken. And the location where it broke is exactly where the beginning, the initiation of the debris flow is. You can see already here some of the tree trunks. Maybe the next pictures will have a little bit more visible. It will be a little bit more visible to see each of those. But what you can see here is that you can at least see 3 different breaches, the primary and the main one, as well as 2 places where definitely water was flowing below the dam, but was not the main place where the dam broke. The next picture shows a little bit of a closer view of the dam. One of our students, who is now a PhD graduate, this is Dr. Jiru Huang. She was a student at Berkeley at that time. She's standing there as scale to give you a sense of what this dam looked like. It's a few redwood tree trunks stacked on top of each other that were placed there. They were positioned there. They were buttressed against other live trees and had formed this dam. The total height of this whole thing was about 16 meters, 45 feet or so. And so it's a very big structure, actually. And maybe the next slide, we'll have a little bit more photos related to this. You can see here a close-up view of some of these tree trunks, some of them reaching, easily 1.5 meters in diameter of each of them. And what Jiru is doing there, she's sitting on one of these secondary, not the primary, but one of the secondary breaches where the water has flowed below the dam. Next slide. These are additional pictures that maybe give you a better sense of the dam. It's easy to think that how much energy will have been necessary to really break in the dam in the main location where it broke. Maybe the next slide. This is a hydrograph-based analysis of what we think at the end happened here in terms of the amount of water that came at the location of the highway. So this is what you have here is on the x-axis the time and dates, and on the vertical axis the amount of water in terms of velocity in cubic meters per second that was coming at the location of the highway. Once you do this hydrograph analysis to see to really calculate for the specific time history of precipitation, how much water should be coming. And what you see here is the capacity of the original 66-inch culvert, what it could handle, the orange, that no longer was operational. But you can also see with the downshoot, the riser, you can see the 36-inch capacity. So in a perfect world, if all the water was below the culvert capacity, we will have no problem. And we have a problem. But the reason that we have a problem is it's not actually that the 36-inch culvert capacity was a bit too low for that event, is that, if you can click the next theme, is that really that the debris flow took out the culvert. And so already we know by that time that the culvert, the riser no longer exists, so there is no capacity. And so from that point on to the next, if you click again, Tim, the water is rising. We know it rose by 10 feet between 8 o'clock in the morning and 3 p.m. There is a witness actually that provided this information. And so at that time, it's still below the highway. The next day, because the storm continues, the highway is actually overtop and the embankment is still there. And if the storm had stopped, maybe that would be the end of it. There will have been no failure. But the storm continued. And then the next, if you click one more time, Tim, thank you very much. You will see that by that time, the embankment has completely washed out and the failure is as you know it afterwards. And so I think that's kind of the whole story of this failure as we documented in this report. Tim, next slide is on you. Yeah.
Okay, so I'll wrap up with the repair. As Dimitrios mentioned, it's about $11.5 million. And a couple of interesting features. First, the fill was placed back in the V that you saw in the beginning. And this was really challenging. You can see this dozer trying to go up the slope and compact the fill at a very steep angle. That's really impressive to drive a bulldozer up that steep slope.
Tim, I think you need to change the slide. I think I'm seeing. Okay, it came to me. Yeah, I can see it now.
Okay. So here's the bulldozer going up the slope, and you can see how steep the angle is on the fill that was placed into the V to bring the highway back up to grade. Here's a photograph. There's the filling in the V and new pavement across the top. In addition to that, Caltrans added a couple of other important features. The first is a row of W24 steel soldier piles that you see right here. These are upstream of the highway. The highway is right here. And the culvert, which I'll talk about in just a minute, is right there. So the idea of these steel soldier piles is to stop the debris and the big trees from reaching the culverts and damaging them. And so it'll be interesting to see if these steel soldier piles are able to withstand the force that's going to come down Rat Creek with these large trees. So in addition to the piles, you can see there are a number of culverts now installed. First is the main culvert, which is 3.1 meters in diameter. So one large culvert, but now there are some secondary and emergency culverts in an effort to prevent overtopping of the highway again, and then erosion of the fill on the downstream side of the highway. So first is a secondary culvert that's 1.5 meters in diameter right here. There's a car on the highway right there. And then two smaller emergency culverts. So if this all fills up, these two emergency culverts, 0.6 meters in diameter, will hopefully transmit enough water under the pavement such that the highway isn't overtopped. So several pieces to the repair. Okay, that's our last slide. Oh, sorry, summary. Floods are becoming more frequent there. As Dimitrios mentioned, there's only 36 years between the last flood and the one in 2021. Clean out debris collection basins as a maintenance activity. So a lot of material does not build up in the basement and the basin, and the capacity remains available to handle a future debris flow. Maintain flow capacity of the culverts, especially after fires. And maybe those steel soldier piles will help with that by trapping a lot of the large debris further upstream. And install emergency overflow culverts as Caltrans did in an effort to prevent overtopping of the highway. So that's our slides. And Santiago, I'm going to stop sharing and we welcome questions.
Great presentation, team. Thank you, Dimitrios. A lot of data, a lot of information to discuss here. And then I'm just gonna invite everybody here to raise your hand and put the questions in the chat. I'll get the questions here in the chat and I'll bring them up to Tim and Dimitrios. But I have a lot of questions, and I'm going to start with one, especially on the repair option. 85 days, almost 3 months, like Dimitrios said, is like very quick repair, in the industrial construction industry. And I'm surprised about this compaction effort that was done by the bulldozers and construction team on this really steep slope. How was that accomplished? Like from, we can put everything on the paper, but just like coming out into actual construction and then doing it, like, I believe, by layers. And then, you need to check, you need to inspect, you need to, kind of accept the feel, right? How did it happen? Were you guys there? Were you guys checking all the time the compaction efforts? What was the engagement there?
Yeah, we didn't check the compaction efforts. Caltrans was overseeing all of that. But the operator operating those bulldozers up that steep slope, remember, right behind you is the Pacific Ocean, right? So you're driving this bulldozer up a steep slope and you look back and you're looking straight down at the Pacific Ocean. That was an amazing operator to be able to handle that.
It's just surprising how they did.
I have to say, obviously this drew the media's attention. It was in the news and everything, but we were there a few days. I don't remember how many days. We have it in the report, but very few days. And Caltrans had already mobilized to start clearing the area. They had to remove a lot of debris first before they fix anything, before they put the embankment. So immediately they were there with a lot of resources, and in fact they facilitated our access to really understand what happened. But they were immediately mobilizing with the intent to. My understanding is that the design was being made while they were still clearing, because they knew they would have to clear all this debris, and they were working at the same time to make this happen quickly.
Yeah,
we were not at all involved. I mean, we had our Caltrans partners, and then we were never involved in anything related to the design or really the construction of this. Yes.
I mean, maybe my question is going to be related to the actual cost of the repair, but why there was not like a proposed bridge instead of an embankment? Yeah, it's like maybe Caltrans will say, well, you know what? Let's just put a prefabricated bridge just coming out of my mind right now. And then, reduce the timing. I know the time was like very, very fast, but still, was that ever considered in the repair?
You want to start? Why don't you start, Dimitrios?
I will say that I know it was considered, and there are places along this highway where bridges have been built. They are more expensive, and my understanding is that they were going to be much slower to build in terms of procurement and everything that was necessary. And without knowing the details, I think that weighed heavily. I have to say also there are other sections of this highway where these bridges exist where debris flows happened also. And the debris flows run below these bridges to the sides. And we can all see that with satellite and actually on the ground. And that were, if there was an embankment there, they will have to have handled it in similar way to what they've done here. But in the case of the bridges, the debris flows just went sideways from the bridge piers.
Yeah, exactly. And this location also had a curve. So you were actually coming around the curve. So it was going to be a little bit of a challenge with the bridge. However, this is a chance I can plug Highway 1. If you haven't had a chance to visit Highway 1, some of the most spectacular bridges, Bixby Bridge, the bridge over Bixby Creek is just spectacular. It's an arch bridge. You see it in photographs all the time. You should go see it just for that. There's another option that Caltrans uses on Highway 1 is the debris shed, where they built basically a shed over top, and so the debris comes down and it goes over the highway and down the other side. So there's one of those just a little further south of Rat Creek, but they determined that the drainage that they were putting in was going to be sufficient.
And that was, that's a good comment because, Rat Creek could be one of those many creeks that we have at Highway 1. Did Caltrans do like any work around the Highway 1 that are kind of concerned about this? Because, we had the wildfire pretty much covering like the entire area. And at this point, I will believe that, any creek after a storm could just have the same issue. There is any kind of post repair work that has been done near the area for for assessing the potential slides or potential failures.
Yeah, go ahead, Dimitrios. You looked at those.
Yeah. I can start. First of all, Santiago, you're right. This is just the section of Highway 1. Highway 1 by itself is 1,000 kilometers. And just the section over Big Sur is about 100 kilometers. There are so many places. And I think the recognition that I think Caltrans has is that this is a system. And along this, the highway is a system. It goes for a long distance and it intersects all these basins. And we in our report, which we didn't present at all today, but if you access the report that we did look and worked with Caltrans to look at other places too. And we have documentation and photos that Caltrans took actually also from all the other places, including where debris flows happen and it wasn't as devastating, places where there was just a little bit of sediment, erosion and scour. This Rat Creek was, of course, the worst one, but there were other ones also that were a little bit threatened, nothing close to what happened here. Rat Creek is the third largest basin actually along that section of Big Sur. So it was already prone to be problematic, and I think Caltrans knew that. And then also because of the riser had a lower drainage capacity because it had basically been damaged from the 1985 storm. And so if you see how much water is coming in versus what type of capacity do we have to drain it out, it was already a weak link. And if you do analysis, which we did along the entire section, you can see that Rat Creek was the weakest link. And that's what happened here. Yeah.
Great. Thank you, Dimitrios. Thanks, team. And I do have a couple of questions here from the viewers. How did you stabilize the steep repair slope? I think that's linked to my first question, maybe a little bit. What is the configuration of the culvert discharge structure? Does it concentrate flow to the Pacific?
Yes. Let me put that back on the screen. Great question. Really great question. I kind of skipped over that. Let me share my screen. There's a pipe or a conduit that takes it further down the slope so it doesn't impact the fill that you saw the bulldozer compacting. Let's see. Let me see if you can see it on this photo. Okay. Santiago, let me see. Can you?
Yeah, we can see.
Can you see these black lines coming down the fill slope?
Yes.
Okay. Actually, maybe I can blow those up. So those take the flow, this one on the left from the big culvert and another one from the secondary culvert. The emergency overflows, I don't remember seeing a pipe also carrying it down because they're much smaller diameter than the big culvert and the secondary culvert. But those little black lines are designed to take the flow coming through the culvert and drop it below the fill material in the rock near the base of the slope. And then it'll go into the Pacific Ocean.
Thank you, Tim. And then maybe the first question was, how did you guys stabilize these steep repair slope? I think you covered a little bit, but maybe if you can expand it a little more. I think the picture that you show with the bulldozer, it's like very impressive. And then everybody's kind of a little surprised how it was done in the actual construction. It was like, I believe it was like a step by steps, going from bottom to top. That's how the sequence happened.
Yeah, just kind of filling from the bottom, coming up, and then the dozer coming up the outside of the slope is sort of at the very end, sort of just kind of compacting the superficial material at the top on surface. Yeah. So just straight fill compaction. There's nothing else. There's no soldier piles or anything in it.
Perfect. And then there's another question. Where the subdrains installed within the field zone? Was there any subdrains installed within the field zone all the way? I think the pipes that are just coming out, I think that's what the question is.
Not that I know of. They started placing fill from the bottom up, and it's just the primary culvert or main culvert, secondary culvert, and the two emergency culverts.
And then that brought up my question, because I see the location of a secondary culvert and the two emergency culverts, the smallest ones. Why don't you guys place it at the bottom of the embankment? I mean, just I believe you guys did a lot of analysis, but maybe catch the water there and then avoid to kind of let it go all the way up. I mean, my thoughts, right?
Well, the biggest concern is the debris flow coming down. I mean, so Rat Creek's coming down. It's getting to the base of the basin, the collection basin, where the main culvert is, and then there's significant fill underneath that main culvert.
Mm-hmm.
So really, those culverts are just trying to handle the debris flow and water coming down the creek versus keeping the fill material from being saturated. If that makes sense.
Yep.
And maybe Dimitrios can explain it better than I just did.
Yeah, no, I think you did really well. Yeah, I think it's clear. But the main culvert, first of all, is 3.1 meters in diameter, which is basically 122 inches in diameter. This is in comparison to the original design, which was 66 inches. And actually what was operated from 1985, which was 32 inches, if I remember correctly. And so we have a significantly higher capacity, but then as it happened in this case, there is a good chance that even the riser will have handled it if it hasn't been completely damaged by the debris flow. So I think the scenario here, and by the way, let me clarify, Santiago, we were not involved in any of this in terms of design. We were just, we were presented and looked good to me as far as I can tell, but we were not involved. But you can see that they're at higher elevation, so that if the primary one gets damaged, there are two spots and not one where actually they will be able to drain the water. So I think that's by design, and I think the same reason, the same thing for the emergency culverts that are just below. The embankment is made out of material that is, of course, erodible. This is not an embankment that's supposed to be overtopped. Once that happens, you're done. And so that's why you have these different elevations with some capacity, so that hopefully you're much more resilient. Yeah.
Yeah. But the other key feature of the repair, I think, are the steel soldier piles, because it's those big trees that came down, not only blocked, but damaged the riser and the culvert. And so if we keep, Caltrans thought keeping those out or away from the main culvert, Dimitrios said it's got much more capacity. It should be able to handle the water flow coming through.
Yeah, those solder piles are really, really important, the upstream side. And there's one other question from the audience here. How were the proposed mitigation measures verified to ensure that they will remain effective and safe under future hazard events, wildfires and storms? Was there any analytical and numerical tools were used in the assessment?
from my perspective, I think I personally do not know what kind of tools exactly were used in design, but I suspect that they did hydrographic analysis like the ones we showed to calculate for different types of design events, how much water it is. One thing that is very, very clear in this case is that you have a lot of redundancy also. You have the main culvert, you have other culverts that are higher elevations. We have the steel, basically the steel piles, that the H piles that are the solder piles that are allowing you to stop the debris. So we have a system here that not only seems to be significantly higher capacity, but also has a number of, oh, if this goes, then this will happen, and if this goes. And of course, the system has to be maintained, right? If you go there and you don't ever clean it up, as Tim said before, like you let it for the next decade accumulate, you're going to have a problem. We have to maintain that infrastructure, and I know that's part of the plan. So they will have to, I don't know how often they will, but they are systematically inspecting the whole highway along the highway to look at what has been evolving in terms of sediments, and they're cleaning up many areas. And so I suspect they will be doing that for this area also.
And then maybe let's go back to the field work and the recon work you guys did. And then when I first did my field work and recon work, I think it was part of the gear, one of the smallest earthquake events that we had in North Texas. You started looking for things that grab your attention. And then one thing that it's important here is that how you guys distinguish the main bridge and the secondary bridges, right, of these tree debris dam, which is, I love the term. It's the first time I hear after I read your publication, the first time I heard about the tree debris dam. I had to kind of dig into it to understand what it was. And as soon as I saw the picture, oh, that's what it meant. But when you're in the field, right, like, let's say like you have a recon team going there, understanding what was the main breach point and the secondary breach areas, how do you guys distinguish these in the field? Was that part of a field assessment, or was the later you guys with, I don't know, aerial views or some sort of other analysis you guys did? That's how you came up with that conclusion.
Yeah. Tim, should I do it or?
No, you go ahead.
Yeah, so I think Santiago, for this presentation, we removed a lot of pictures, and I realized after that there were actually some very clear pictures of the breakage points that we didn't show today. It's definitely in our report. Maybe that's a reason to get the report. When you're there, you see this dam and the main bridge, in the main bridge area, the tree trunks have moved. They have kind of exploded, like they are kind of like a brittle type of failure that they have exploded, and it's also where there is the biggest scour depth there. It's very, very clear that this is the spot. The other two, I don't know if I contributed in calling them breaches, but maybe, there was water seeping and eroding below the dam. It's not clear there was an actual breach, but there was definitely water going in that direction. But the main breach is extremely visible. We also did LiDAR scans there in that area, and so we had a very detailed geometric. And when you see it all together, it's very, very clear where the main bridge is. For example, on the side of where basically the lake had formed, when the breach happened, the tree trunks are scoured. There is no bark on, is the bark what we call it? Yeah, the bark on the tree has been washed out because of how the water and the sediment was moving through this bridge, and has actually stripped basically the exterior of the tree trunks. And so when all that stuff, I think, is very clear in the report also, but definitely if you're there, it's very, very impressive. It looks like very intense when that happened, for sure.
Yeah, I saw a few pictures. Yeah, I think it's I think it's the field impressions and the what you see is what's actually the meaning results on this. So it's great to have those pictures. Yeah. And then I don't know, Tim, you wanted to add something? Did I cut you off?
No, that was great. And again, the scour was a lot smaller or shallower
Yes.
on the secondary and
Secondary.
tertiary. So it was pretty clear.
And then I do have another question, kind of similar to the investigating different sites we discussed initially. Similar conditions to the Grizzly Creek debris flow Glenwood Canyon in 2021 damaged the I-70. Do you recommend investigating sites with similar conditions and installing debris flow protection measures? I think we all
Go
will
ahead.
agree with that. Maybe
Go ahead,
Dimitrios.
Dimitrios. Because Cal
Yeah.
says, yeah.
I think overall, and I see that maybe, I don't know how much time we're going to have. Maybe the main message that I personally have is that these type of assets are distributed, are long, but they are affected by activity and things that are happening further away from them. An inspection along the highway only may not be enough. Now, it is impossible to be walking up all of these areas just because we're looking for some evidence, but I do think that the technologies that we have, like the ones we applied here, and there are additional ones, do allow us for a better assessment of potential areas where something like that has happened. Whether it's satellites or UAVs or even terrestrial scans, of course, the terrestrial scans are smaller areas. I think there are technologies now that can allow us to really reassess the conditions and realize that this is a dynamic system. You know, when you have a wildfire and then a storm, the conditions are not the same the next year as they were before. And we need to inspect, and I think technology and AI can help us do this very, very efficiently in a way that was actually impossible before. We all know how much pressure there is on all these authorities to maintain this huge infrastructure. But I think there's a good message coming up with the technology that we have now. But the answer is a quick yes, that we need to do that. Yeah.
Yeah, and I think Dimitri's analysis that showed the amount evacuated from the Rat Creek area can be used to show how quickly the collection basins are filling up. And that might be a quicker way to assess all of these. As you said, Santiago, there are a number of these down Highway 1 and other highways, like somebody said, Glenwood Canyon. So you can take a LiDAR at 1 year and then compare to future LiDARs and see how much is building up or not building up in these drainage areas.
Yeah, LiDARs provide us with a lot of information nowadays. It's a very, very useful tool that we can take advantage of. There's another one, maybe it's already linked to this, to what you just said, Tim. Is there any plan to monitor the slopes that lost vegetation during wildfires to plan remediation or evacuation or any risk management strategy, right, for the rainfall season? Pretty much what you just commented.
Yeah, I think Caltrans is monitoring the slopes on Highway 1, but I think we could use more remote sensing techniques to help facilitate that.
And then what could be, and this is one of my questions, what could be one of your advices to give to younger geotechnical engineers that are about to conducting recon work after an extreme event like this? I know they're going to be with a hands-on to the site and the tools they have available, but what would be your advice as an expert? Experts in this field.
Yeah. Okay, Dimitrios, you want to go first, or you want me to go first?
Please go ahead, Tim.
Just advice to young people doing some reconnaissance. Bring a really good pair of boots and be prepared to walk a lot up slopes, across slopes, down slopes. Some of the photos we showed didn't really show how tortuous walking up Rat Creek was, but there are going to be little places where you kind of got to hop up and get over things and get to different places. So bring some clothes you don't mind getting really muddy and dirty, and you may not take them back home with you, but bring some good equipment, good camera, some measuring devices. If you have some of the remote sensing technology that Dimitrios talked about, would be helpful too. And just be observant, look around. Like Dimitrios showed photos of the scour depth, that's really important. People could just walk past it. The other thing is the mud up in the trees. Everybody's kind of walking, and we're geotechnical engineers, you're always looking at the ground. Look up because there's a lot going on in an event like this up high. And Dimitrios showed several good photos of that. And that's how he determined water level and also splash height. So go ahead, Dimitrios, why don't you jump in?
No, I think, Tim, you covered it very well, of course, with the experience you have. I will say, I will add to this about staying safe. These are areas that can be dangerous. In our case, we had, in this case, very specifically, Caltrans people accompanying us, and because also they were worried about what we're going to do in terms of being safe. And in general, being safe, being also with a team, people see different things based on their experiences. If you're the youngest person, it's good to go with some of the more experienced colleagues who have seen a few things. Learn to observe. I think that's a big thing that Tim said. I think it goes back to the heart of the observation-based methods that Terzaghi has advocated for. And also, sometimes we have biases about what we think is happening, and what happened, and the story may be different or in addition to whatever you thought was additional things. And so being open eyes, open ears, talk to people there. Get involved with GI technical communities with gear that is actually doing deployments like this, and so you can actually get engaged. It's very, very important in terms of documenting really just after the disaster what happened, how things moved. It's information that is perishable, and we need to if it's not collected then, it's going to be too late later. Yeah. So it's an important job, actually.
Yeah, and it's amazing how much we learn from these type of events, like similar to earthquakes, similar to landslides. After what we learn and after what we document, I think that's where the lessons are taken from the industry, and the new methodologies, new techniques are being developed. So it's just amazing. Maybe one last thing, I would just say, adding to your comments, maybe doing some pre-field activities also help. Trying to understand the site, trying to get the aerials of the site. We have a lot of tools available nowadays that can help us to before going to site, understand a little bit more where we're going to assess the field work. Maybe one last question from my end, and then maybe I can let Brad taking over. Does this work give you any uncertainty, that remains in your mind? I don't know, the timing of the tree dam breach, for example, or the debris volume. I know it was very, very accurate, calculated with LiDAR. Maybe the rainfall intensity, any culvert blockage that you guys think, any kind of uncertainty that you think, this might be like a need of a deep, closer view to understand a little better future events.
Yeah, absolutely. I think we collected a lot of evidence that is helping us constrain some of these uncertainties, and there is nothing that is certain at all for sure. But I think when you start narrowing it down, you start pointing out to what is the most likely and most predominant and probable, or definitely a mechanism that needs to be considered in the future. I think I never feel that I have everything. This is a dynamic phenomenon that had peaks and troughs in terms of precipitation, velocities were evolved. And even if we go there immediately after the failure, we're still watching what really happened at the very end. And in the case of storms like this or breaches, You only have the data at the very end, and there is a lot that happened throughout. It would have been amazing to have installed cameras, to have sensors, but of course, the nature of where this happened, it was definitely impossible. But we'll see in the future, because this technology now allows us to, at least for the most critical places, to have inexpensive sensors that could help us get better insights. And when you have better insights, you should be doing also better. We can do better modeling and more sophisticated analysis that may be warranted. But yeah, I think we just narrowed the uncertainty. We didn't eliminate it for sure.
Perfect. Thank you, Dimitrios. Thanks, team. Thank you, Dimitrios, again. I don't think I have any more questions from the audience. I have Brad right here jumping in, and then I'm really honored to talk to you guys. It is amazing work that you guys did. Brad?
Great. Thank you.
That was great, guys. Thank you so much for this. And I will confess, I was like, oh man, we're doing another thing on disaster reconnaissance. But I think what you guys added to it, it wasn't that simple, I guess, is the easiest way to say it. So very cool presentation. And thanks to all our viewers, especially the people who asked questions today. We got a ton of questions. That was fantastic. That's really what gives these sessions their vibrancy and that back and forth. And it adds a lot of value for all of us, I think. For all of our viewers, I put it in the chat. Our next live stream is in 7 days. We're going to be right back here with a live episode of the Geo Legends series. We'll be celebrating the life and career of Chuck Ladd, who spent his entire life, it seems like, at MIT. We've got a crack expert panel coming to you, a lot of Massachusettsans. I don't know what they go by, but a lot of people from New England, and then some people who have gone farther afield. Mary Nodine, Geostrata editor extraordinaire, will be hosting that and running the interview panel. So it should be fantastic. Registration's always free for our live streams. You can get to all of them on our Eventbrite page. And a reminder, if you liked what you saw today and you're here at the end, so you probably did, click like, subscribe, and get notifications. And yep, we'll let you know every time we post something to the YouTube channel. Santiago, great job. Your first time in the moderator chair. It was wonderful. Tim and Dimitrios, we see you guys a lot, but you still did a good job. It was still an excellent presentation, and you had answers for all the questions, so we thank you. And our producer today was Aurora Flieger, and we will see everybody really soon with another Geo-Institute live stream.